Hello, this is Jaromír Mastík from the MicroRisk company, and I'm going to introduce you to the IQRF technology basics. During this presentation, you will learn what is the IQRF and how to use it, what are the typical applications. I will talk about IQMESH network and DPA protocol, how to create network, how to manage network, and so on. I will also talk about transceiver module as a basic piece of this technology. And finally, you will learn how to start with IQRF, where is the right starting point. The IQRF is a wireless platform working in ISM bands 868, 916 and 433 MHz. It is focused on low speed and low power and low data volume packet-oriented communication. The basic part of this technology is a transceiver module, shortly TR module, with built-in operating system. The main advantage of the IQRF is the support of mesh networks up to 240 hops for one packet. The final functionality of the TR module depends on the uploaded user application. The RF range always depends on the hardware design, but in general it is tens of meters in buildings and hundreds of meters in open space. The IQRF is also suitable for low power applications. The TR module can be put to full sleep or to the special LP mode while it is still receiving, with the average consumption about 250 microamps. The IQRF uses low data rate about 20 kilobit per second. The platform is intended for packet-oriented communication with up to 64 user bytes per packet. And of course, there are no license fees. The IQRF is a complete ecosystem. It is not only TR modules, but also development tools, accessories, and ready-to-use devices like gateways, repeaters, sensors, actuators, and so on. We also provide IQRF Gateway daemon for Linux-based machines, like for example Raspberry Pi, or IQRF SDK for devices without operating system, like for example Arduino. There is also a lot of demo examples provided. The IQRF Alliance is a group of cooperating companies working with IQRF. The result is a portfolio of compatible devices that meet the IQRF standards. All these compatible devices are included in the database, which is called IQRF repository. Typical applications are lighting systems, sensor networks, building automation, or in general, all applications where there is a need to control something or collect something using short packets. Here you can see a typical network application. There is a mesh network of any devices. The end device we call a node, and the master of the network, which can be only one, we call a coordinator. All TR modules must be uploaded with a DPA plug-in with the given functionality. The coordinator is typically built in a gateway based on the IQRF Gateway daemon. The daemon supports communications with the IQRF IDE for some service purposes and with the IQRF repository to know all compatible IQRF devices. For the user, there is available a documented API interface, so a user is able to create applications communicating with the IQMESH network via MQTT or WebSocket protocol with data in JSON format. As I already mentioned, the final functionality depends on the uploaded user application, that is the second layer above the operating system. And there are two approaches. The first one we call C programming. It is intended for non-networking peer-to-peer applications. In this approach, the user must write a complete application in C language. The second approach is intended for networking. It means IQMESH applications. In this case, a user uploads ready-to-use DPA plugins with the required functionality. This is the blue part of the memory in the picture. The green part is a space for so-called custom DPA handler that must also be written in the C language. But a user doesn't write main loop of the code, but handles events provided by the DPA plugin. The basic development kit is the CKUSB 04A. Anybody who plays with IQRF needs at least one. This kit is typically connected to the IQRF IDE via USB and works as an uploader, debugger, or as an USB gateway for the network coordinator. The second basic kit is the DK-Eval 04A with the accumulator inside. We also provide extension kits that can be connected to the DK-Eval kit via the side connector. There are 3 kits with 6 buttons and LEDs, with 2 relays, and with sensors like temperature meter, potentiometer, and light sensor. The basic development set is the DS-Start 04 that contains 1 CKUSB kit, 2 DK-Eval kits, and 3 TR modules with integrated antenna. The DS-DPA 02 set consists of 2 DS-Start sets for a better price. So it was hardware tools. The software tool is called IQRF IDE and can be downloaded from the IQRF website for free. This tool allows to compile, upload, and debug a user application, offers a richly equipped terminal, and many other tools. The IQRF IDE allows to set and upload TR configuration. On the left side, you can see parameters related to the operating system, like RF band and channel. On the right side, you can see parameters related to the DPA plugin, like RF power and sensitivity settings, and many others. Very important is the security. The IQMESH uses so-called access password to access given network. In other words, to be a node able to bond to a network, it must have set the same access password as a given coordinator. The default access password from the factory is 16 zeros, and it is recommended to change it using this configuration window. Here you can see the terminal window with the possibility to create macros. When you double-click a packet in the log, the packet inspector is opened and you can see an interpretation of all bytes, including links to the online documentation. Probably the most useful tool in the IDE is the IQMESH Network Manager that allows the management, testing, and visualization of the IQMESH network. This tool is built above the terminal, so a user can simply check what DPA packets were used on the background to do some specific task. Let's talk about the IQMESH. The IQMESH is a protocol implementing a mesh routing. Every IQMESH network consists of 1 coordinator and up to 239 nodes. From the power consumption point of view, a node can work in standard or low power RF mode while receiving. The standard mode is typically intended for devices powered from mains. The low power mode is power saving, intended for devices powered from a battery. This RF mode uses longer time slots per hop, so the communication with LP nodes is about 2 times slower. The RF mode is specified by the uploaded DPA plugin. There are 2 network types available: an STD network that is faster and works with nodes in standard mode only, and STD plus LP network that is slower because of longer time slots per hop. This network type works with nodes in STD as well as LP mode. The network type is specified in the TR configuration of the coordinator. The routing is based on optimized directional flooding and TDMA. And because every node can also work as a router on the background, the network supports up to 240 hops for a packet. The basic communication in the network is synchronous. Typically, the coordinator sends a request and the address node sends a response. Such communication requires nodes in receiving mode. For applications with battery-operated devices that sleep all the time, the IQMESH offers so-called beaming. The beaming node is sleeping all the time and periodically or on some event asynchronously sends data to so-called aggregating repeaters in direct RF range. The aggregating repeaters store the received data from every beaming node into the buffer. The data can be then read out synchronously by the coordinator. All communication is automatically encrypted by AES-128. This picture shows the RF packet from a security point of view. The black color is user data that can be optionally encrypted by the user key set in the TR configuration. The blue color is packet overhead generated by the operating system. It is divided into blocks where every block has its own checksum. The green color indicates the packet consistency check by CRC, and finally the orange color indicates the packet encryption using AES-128. How to create the IQMESH network? The first step is uploading proper files into TR modules. It means a DPA plugin with the required functionality, correct TR configuration and optionally a custom DPA handler. In this step we have created a coordinator and some number of nodes. The next step is including nodes into the network. This process we call bonding. During bonding, the coordinator assigns an address, network key and some other information to node. A node to be bonded must have set the same access password as the coordinator and must be in unbonded state. The IQRF supports several bonding ways, like using a button press on a node, by a reading of QR code or NFC from a node, or using a special bonding tool called IQIP. The most sophisticated is the Autonetwork process that will be explained later on. When all nodes are bonded, they can be installed. To be the IQMESH network working well, it is important to be every node in a range with more neighbor nodes. If there is place with weak RF correction, it can be covered by a dedicated repeater. After the installation, the coordinator must learn the topology of nodes to create the routing structure. This process is called discovery. The discovery is a time-consuming process. It can take several minutes. The time depends on the number of nodes and their topology. Only nodes with routing enabled in the TR configuration can be discovered. In other words, only discovered nodes can route packets. The routing structure is static. It means that if any discovered node was moved, removed from the network, or added to the network, the routing structure was changed and a new discovery process should be called. During the discovery, the coordinator also virtually readdresses nodes to so-called virtual routing numbers that are used internally for the routing and the user needn't know them. In the last step, we should test communication with all nodes, do network backup for possible future exchange of the coordinator or a node in case of failure. The following animation shows the routing. The white numbers on nodes are bonded addresses and the yellow numbers are the virtual routing numbers assigned during discovery in the increasing order from the coordinator. So as a first, we'll route packet the node with VRN1, as a second we'll route node with VRN2, and so on. The other C in this animation is the yellow not discovered node. Now I will start the animation. You can see the redundant packet delivery on every routing node. And finally, the other C has received the packet 3 times in different time slots. The time slot length depends on the RF mode and the packet length, and it is from 40 to 100 milliseconds. The IQMESH implements several communication types. The fast response command, shortly FRC, is a very useful communication type when there is a need to collect small data from many devices. The FRC allows to send a request to all or selected nodes and collect the following data: 2 bits from all 239 nodes, or 1 byte from up to 33 nodes, or 2 bytes from up to 31 nodes, or 4 bytes from up to 50 nodes. The limitation is given by the internal RF buffer size, that is 64 bytes. The FRC consists of 3 phases. In the first phase, the request is broadcasted to the whole network. Then, every node, one by one, sends its data locally, and these data are received and stored by all discovered nodes in the direct range to the given node. In the last phase, all discovered nodes, again one by one, from the highest VRN, send collected data back to the coordinator. One of the most complex and sophisticated features in the IQMESH is the Autonetwork. This is the automatic network creation process that can be launched after the installation of all nodes. Shortly, it is a process that involves the bonding and discovery of all available nodes with the same access password as the coordinator. The Autonetwork consists of so-called waves. The number of waves mainly depends on the number of nodes and their topology. In the first wave, the coordinator tries to find all nodes in the direct range, bond them, and finally makes a discovery. In the second wave, the coordinator tries to find all nodes in the range to nodes that are already in the network, and so on. The process finishes when no new node is found or after the network contains a specified number of nodes. Finally, the network is enumerated, so the host system connected to the coordinator knows which device types are in the network. As I already mentioned, the IQRF offers a special communication type for battery-operated devices which are sleeping all the time. In this picture, you can see 3 yellow, not discovered sleeping sensors and 2 blue repeaters with the aggregating functionality. Every sensor randomly on some event wakes up, sends data, and goes back to sleep. Data are received by aggregating repeaters in direct range, stored in a memory, and can be read out by the coordinator using the FRC. For service purposes, the IQRF offers the so-called DPA service mode, shortly DSM. The DSM allows connection to the coordinator or any node in the direct RF range using a special tool available in the IQRF IDE. This tool is called CATS and can be created from any TR module connected to the IQRF IDE. To be the connection with the network device possible, a user must know its access password. Then just reset the device and the DSM connection will be established. The DSM connection is kept until the next device reset. During the connection, there is a communication pipe for any DPA request, so it is possible to bond or unbond the device, change its configuration, upload a new DPA plugin or custom DPA handler, and so on. To end the DSM connection, just reset the connected device or click the disconnect button in the IQRF IDE. Now let's talk about the DPA plugin. The DPA means the direct peripheral access. It is an application written by our company, and the final hex file is encrypted to a file with the IQRF extension. DPA plugin is a ready-to-use application with embedded peripherals and services. There are 4 basic plugins: for a coordinator with the SPI or UART interface, and for a node in the standard or low-power RF mode. All peripherals and services are documented, so a user may find out that the implemented functionality is enough for his needs, and in such case there is no need to write any code. In case of need to add any functionality or modify the default behavior, it is possible to write a custom DPA handler. In the handler, a user can handle events provided by the DPA plugin. There is a lot of events provided, for example, after reset, after a request was received, before the response is sent back, and so on. All functionality of the DPA plugin can be controlled by a simple byte-oriented protocol called DPA Protocol. This protocol can control all peripherals and services of the coordinator or nodes, can create and manage IQMESH networks, and also offers very sophisticated features like over-the-air upload of the operating system, DPA, and custom DPA handler. The DPA plugin supports the SPI or UART interface to connect the coordinator to the host application. The protocol itself is very simple. The first part is the network device address. It is possible to address the coordinator, any node, or all nodes using a broadcast address. There are 2 bytes for the addressing, but only 1 byte is used. The second is reserved. The second part is the peripheral number. It is 1 byte that specifies the code of any peripheral either embedded in the DPA plugin or implemented in the custom DPA handler. The peripheral can be, for example, LED, UART, I/O pin on the TR module, and so on. The third part is a peripheral command. It is again 1 byte long and specifies a command of a given peripheral. For example, in the case of the LED peripheral, the command is set on, set off, pulse, and so on. The next part is the hardware profile identification. These 2 bytes uniquely specify the type of the device and its manufacturer. The hardware profile ID is assigned by the IQRF Alliance. The hardware profile ID can be also used for the packet filtering. For example, if you have a network with lights, blinders and temperature meters, and you want to do something with the blinders only, you put hardware profile ID of blinders to the DPA request and send it as a broadcast. If there is no need to do such filtering, the value FFFF should be used. The last part of the packet is optional, and it is a space for up to 56 bytes. For example, if the peripheral will be the EEPROM and the command will be write, here is the space for the EEPROM address and the data to be written. Here you can see possible addresses and example of peripherals and their commands. The coordinator has always the address 0, then there is a space for 239 nodes, and the broadcast address is FF. So if the task would be to switch red LED on at node 5, the request should look like this. The node address is 5, the peripheral number is 6, which means the red LED, and the command for the LED is 1, which means the switch on action. The hardware profile ID is FFFF because no filtering on hardware type is needed, and the data part is empty because no additional data is needed. This slide shows a real application where no programming is needed. The TR module is connected to the lamp via UART, and because the UART is one of the embedded peripherals in the DPA, no programming is needed. The lamp can be controlled by the request with the UART peripheral and command write. And as a written data, the communication protocol of the lamp itself is used. The gateway is based on the Raspberry Pi with the IQRF gateway daemon installed. The coordinator is connected using a proper shield. The user controls the network via MQTT protocol with the data in JSON format. So the integration of the mesh networking has never been easier. The basic part of the IQRF technology is the TR module. Every TR module contains MCU with operating system, RFIC, external EEPROM, and other components that differ according to the module type. These components are mainly the voltage regulator, temperature sensor, LEDs, and antenna. The user can choose a TR module according to the antenna solution. There are three options: TR module with the integrated antenna, TR module with the antenna connector, or TR module with the soldering pad hole. There are also three mounting options. TR module can be inserted to the SIM connector, and TR modules intended for soldering in the horizontal or vertical position. Here you can see a comparison of block schematics of TR-72D and TR-76D modules. The TR-72D module is intended for the SIM connector. It has 6 I/O pins and contains the temperature meter, 2 LEDs, and the LDO voltage regulator, so it can be supplied from 5 volts. The TR-76D module is intended for soldering. It has 11 I/O pins and has no LEDs, no temperature meter, and no LDO. This module can be supplied from 3 volts. This is detailed schematics of the TR-72D module, which is intended for the 8 pins SIM connector. 2 pins are for the power supply and 6 pins are I/O pins for general use. These pins are connected directly to the MCU. As you can see, some pins are connected in parallel to have available more MCU peripherals on the SIM connector. The TR-76D module, intended for the soldering, has no pins connected in parallel, but all are available on the soldering pads, including pins controlling LEDs. So a user can design the device with LEDs visible on the box. The usage of LEDs is strongly recommended because of operating system, and also the DPA uses some system indication, for example bonded or unbonded state, factory reset, TR programming, and so on. So how to start with IQRF? You need one of the development sets and startup package for the operating system version you have. The startup package can be downloaded from the IQRF website section Downloads. The startup package contains everything you need to start. The best way how to start is to go to the IQRF website menu How to Start. There you will find the step-by-step procedure, including a lot of video tutorials. All information related to the IQRF you can find on these two websites. In case of any technical or sales questions, you can contact us on the support or sales at iqrf.org. Thank you for watching.